Okay, so the next thing that we're going to do is we're going to start chapter 8. And chapter 8 starts the part of the course that is about the design of analog integrated circuits. And that really is essentially op-amps. With op-amps, we can do a lot. And as I have mentioned, when we are designing for integrated circuits, we have to look at things a little bit different in what we can do with the proven fabrication techniques, reliable fabrication techniques that we have. And chapter 8 is about the building blocks of this analog integrated circuit. So we're going to see which are the building blocks. And then in chapter 9, we put it all together. And in chapter 9, we actually design an op-amp, actually a pretty good op-amp. So let's look at so this is chapter 8. And these are building blocks of integrated circuit amplifiers. And the first thing that we have to do is look at the design philosophies for integrated circuits. First thing, the one thing that we can do well is design transistors or fabricate transistors. Okay? So what we need to do is minimize the usage of resistors. We don't like resistors. We can fabricate resistors, but not as well as we can fabricate transistors. So we like lots of transistors. In that sense, a better design is not one necessarily with fewer transistors, or fewer components overall. So we're going to, if we need to throw transistors at things to get rid of resistors, and you saw that in the concept of switch capacitor filters, we're going to do it, okay? Point number 2. All we can do is for sure specify the width, the electrical width of the channel, which is the geometrical length of my transistor. And also we could specify the channel length and the width of the transistor, but I'm going to put an asterisk here because I'd rather keep this constant, because the process is optimized for that critical dimension, which is the width of the polysilicon, the geometrical width of the transistor, which is the electrical length of the channel. So unless it's really necessary, I don't want to make the transistor geometrically fatter than it needs to be. I can make it as long as I want geometrically, but I want to keep that critical dimension, which is because when they do the process control, this is a fabrication or manufacturing process control, they're going to target a number here, okay? They're going to target a number there. And if I deviate, then I'm giving up, let's say, reliability of fabrication, not reliability as in that it's going to break, but that I'm going to hit that the target that I'm requesting. It's being optimized for a specific number, okay? So since I want to, and this is point number 3, since I want to get rid of resistors, which I really use for biasing circuits, okay? We, instead of resistors, are going to be using current sources to bias. And so you can imagine, to get rid of one transistor, I'm going to be designing a current source with several transistors, and that's great because we know how to make them. They're cheap. We can make lots of them. So use current sources as loads, as loads, and for biasing instead of resistors. Now, if you can never say never, if I do have to have resistors, okay? So if resistors are necessary, I need to know that in the technology of fabrication, a small and accurate. Small and accurate is difficult. Small and accurate is difficult. Now, in reality, we can do anything, but when we say difficult, what that really means is expensive. And again, everything is in the context of a business. So we don't like difficult because difficult is expensive. Now, what we can do, because we cannot get accuracy, what we can have is precision. So I cannot be right, but I can be very well consistently wrong. And if I know that I'm wrong all the time and by how much, I can correct for that. I can calibrate, I can do a number of things. So we're always going to be favoring precision or repeatability instead of some type of accuracy that is how close I am to some absolute target. So since I can be precise, if I, instead of relying on absolute values, I can rely on ratios, then the inaccuracy is going to cancel each other because I'm going to be always wrong in a very well controlled manner by some amount, but that delta, that error, if I rely on ratios, is going to cancel. And since the precision is well controlled, then I can get good accuracy from a ratio perspective. So that's very important. So that is going to be point 4A here, that ratios can be obtained with narrow tolerance. So if I have two components, okay, if I have two components and the value here at 100% accuracy, and I have another one, so this is, let's say, component 1, this is component 2, and this is, they have to have some specific value. Absolutely, I'm not going to get it. I'm going to be getting some, let's say, on the scale of percentages, let's say I get here 110%, but it's going to be very repeatable. The distribution is going to be very narrow. And then this one also is going to be, that error is going to be very reliable and narrow. So if they are consistently both components 1 and component 2, 10% off, the ratio of component 1, the value of component 1 to component 2 is going to be very accurate. So if I make my design depend on that ratio rather than on the actual value of one of them, then I have a design that is very accurate and precise. So making designs that are that rely on ratios is very important. So that's one of the techniques that we're going to be using. All right, so point number 5, when it comes to analog integrated circuit design, we want to avoid large capacitances. Okay, we're going to avoid large capacitances. We can make good small capacitors because, again, just tying that, we can make transistors, and tying the source and the drain of a transistor will form a capacitor with the gate as the other electrode. But since really we don't want to make these big transistors and have big capacitors, we avoid large capacitances altogether. And what that means, what that really means from a circuit design, is that we have to avoid coupling. We have to avoid capacitive coupling and decoupling. Remember that we are talking about analog design and about signals. So we have to couple and decouple. Normally we would couple and decouple signals with capacitors, you know, the AC signal from the DC biasing points. But in IC design, we don't do that because we cannot afford the large capacitors that would be needed. Okay, so what that means, so circuits are directly coupled. So that presents a design challenge. Okay, so we'll see some techniques to do that. We'll see techniques. For that, for coupling and we also will see techniques, because when you are coupling and decoupling, what you're doing is establishing a signal ground. So if you remember on the common source, that we have that source resistance, and from a signal perspective, we decouple that node with a capacitor, right? That was to establish this as a signal ground for the signal, but we still wanted that node to have a DC bias to compensate and give us some GM control, or not GM, but the gain control for the transistor. So we're not going to be able to do that. Okay, so now this point is not going to be a signal ground as we would like, as it would be ideal, and that that presents a design challenge. So we'll see techniques to establish signal ground. So again, just a small C. We can do that at easy because we're making with transistors, and because of what I explained before, we can make it with precise ratios. Okay. And a final point. We're looking at very advanced, very small. So we want the nodes to be small, the transistors to be small, because then we can put more on the same area and fabricate more transistors with the same planar fabrication step. So we like that the transistors are small. However, these are real materials, and these are real, for example, the oxide. The oxide, which is the layer of oxide that sits between the channel and the actual gate electrode, the polysilicon. So that's in your transistor. Again, I'm going to be tired of seeing this type of drawing. So here's where the channel will get enhanced, and here is the polysilicon layer here. So kind of like a 3D thing going there. But here there is an oxide. So this is polysilicon. This here is oxide. And this is the thickness of the oxide. Okay. So if you put a voltage at the gate on the polysilicon electrode, you're going to get an electric field through that oxide into the channel. There's going to be an electric field, okay, which is going to be that quantity. Well, this dioxide here is in the order of angstroms. That's how we measure that. They're really thin layers of oxide. So if this dioxide is small, what that means is that for regular voltages, you know, whatever it is, it doesn't matter. This is a huge electric field in the millions of volts per meter. So that puts a stress and can put a stress on that oxide. Okay? From a material perspective, I mean, fields is energy. So we have to try, we want these dioxides to be small because the transistors are small. We want to try to work with as small voltage as possible. Okay? So my point number 7 is that, you know, use a small VDD so to deal with a smaller device, smaller devices. and thinner oxides. So since VDD is small, and we're still talking about silicon, because silicon is inexpensive. I mean, we can use, I told you about other materials and compound materials like silicon carbide, gallium nitride, but silicon is the one that is the cheapest. Okay, we don't have to make them. We just go back to the beach and grab sand and purify it, and we have all the silicon that we want. So we're talking about silicon, and there is nothing that we can do about our threshold voltage. So our threshold voltage is going to hover, around 0.6 volts. And that's a function of the material. That is a function of the work function of the quantum mechanics of the material. There's nothing we can do about that. Therefore, if we cannot change VT, but we are reducing the supply voltage, that means that our overdrive voltage that we can be above VT before we get to the VDD is going to be really small. So that's going to be in the range of 0.1 to 0.2 volts, okay? Because we want to work with the small VDDs, VDDs that are for modern designs, okay? For modern designs, internally, to deal with the small transistors and oxide that we don't want to stress with high voltages, we're going to have VDDs of 0.9 to 1 volt, okay? So that is a design challenge, mainly when it comes to the presence of noise and how we deal with our noise margins and noise floors and things like that. So lots to learn when it comes to integrated circuit design. So everything that we do in terms of decisions for design are going to be in the context of these principles that I have outlined here. So any questions so far? Any question at this point? Or anything that you want me to go back to or elaborate on? All right. Okay, so then let's go next to the next section, where we're going to start looking at different blocks for constructing these integrated circuits, these analog integrated circuits. And the first thing that we need to do is be able to bias the transistors. So the first topic is going to be on biasing. And we already said that we are not going to use resistors. We're going to use current sources. So we're going to look at current sources. And in that context, also current mirrors. Okay. So I'm going to share what we mean by that. So what I mean by that is this type of topology. Okay. Now, if I get myself so with one resistor, okay, with one resistor, I'm going to set different biasing currents with current sources using a current a topology like this, okay, and here we have two transistors and essentially a current mirror to get an output current, okay. Now, I do have to consideration what this is driving, because I have to make sure that Q2 is saturated, operates saturated. And I can get the right, remember that a lot of the design and explanations of these topologies is just to get design equations for the width, the electrical width of the transistor. So I can then draw my transistor when I'm doing the design of the integrated circuit. That's all, okay? So this is the one that we're going to be looking at, okay? So refer to figure 8.1 in your books as I'm going through the derivation here, okay? So for that circuit, so again, that's figure 8.1. So for that circuit, if I look at the drain, the drain current for transistor 1, I can write that equation, and they're both N channels. So this is kind of a good segue from that problem 1250 that we did using the same. If you go back to that topology, I established a reference current from that good transistor that I got me fabricated. I want to use many of them, just one. I can write that drain current is the reference current, okay? And that is going to be the supply voltage minus VGS divided by R, okay? And we can do techniques to get, we do need a good value of R, but there are techniques to do that, but I just don't want to have to apply those techniques in 10 Rs, it's just this one. Now, similarly, I can write the drain equation for transistor 2, and that's going to be my output current. Remember what K prime is. That involves the GM of the transistor, the capacitance of the gate oxide, the mobility. So all these things that go into the GM of the transistor. So, but mainly the mobility, the gate oxide, the gate capacitance of the oxide, and all that. So there's nothing you can do about the K prime. And that's why we distinguish K prime from K, because K prime is, K is K prime times the ratio. But we can adjust that, essentially the W's, and that's what we're trying to come up with. Ideally, you want design equations that are in terms of the ratios of W's of different transistors. That's really a good design, the best type of sort of optimal design philosophy. So that's my second equation. And if I have, so remember that to get a good value of Iref, I do need a good value of R, but then all I want to do is derive all different currents to do all different kinds of biasing in my design as a multiple of that Iref. And then I know I'm good, because if I just play with that R and get a good IREF value, and then all the other ones in terms of ratios of that IREF, then I can get good values for those two without having to mess with anything else, just by tweaking or by changing the value of the W's. So if I look at, if I get a proportion for this current source of IO, or the output current in terms of IREF, I can write that the output current over IREF is going to end up being just the ratio of these two ratios for the transistors. And as it would be, as it usually would be, if L1 is equal to L2, then I have the ratio of the current as a ratio of the width of the transistors or the geometric length of the transistor. So now I can set any output current that I want, and if this is a good value, by just having the appropriate ratio of the widths of the transistors or the electrical channel of the transistor, I can get good values of output currents for whatever I want. Okay? So that is a very simple current source. So I can write that the current in transistor 2, which is my output, is, and this is my reference, times that reference current that we know is VDD minus VGS divided by R. Okay. Let's look at another couple of figures as we start evolving these blocks. So that gives us the basic MOSFET current meter. Okay, but we'll start looking at it that way, and then if I can get the current that I want, then I can get output voltages as well, and I start using this for my biasing networks. The output characteristic of this type of current meter is shown here. So here you have the ratio of the width to length ratio of transistor 2 to 1 times the IREF is right here. Okay. So that's what you start after your output voltage goes above VGS, then you start getting sort of a constant current characteristic. So essentially, what is a constant current source? That, you know, the voltage changes at the node, but the current doesn't. So you start getting that at this point over here. But it's not so ideally, you would want a slope of 0 or a flat curve or horizontal curve. That would be an ideal current source. But you don't. And the reason you don't is because that transistor Q2 has an actual output resistance, the transistor itself, that cannot be ignored. So the slope that you get is actually 1 over that output resistance of Q2. Now, you would like that output resistance to be as large as possible so that you don't, so basically you can deliver that current to the load, and the slope then is as flat as possible. But there's going to be a very small slope of and that's due to the output resistance of the transistor. So that's important to keep in mind. So essentially, with these techniques, with these types of mirror, you can derive all kinds of currents that you need just by changing the ratios from some reference. That's also, that technique is called current steering. And there is a nice graph here, okay? Where essentially you have from this reference here, you derive an I2 here, and then you can then use that to derive an I3 here, which you use with some other current mirror to derive an I5. And all these currents are related to IREF. All these currents are related to IREF through ratios of transistor or channel width or transistor geometric lengths. So you're just playing with the drawings of the transistors as you make the integrated circuits. In fact, there is a very popular digital to analog conversion architecture, which is called current steering DACs, that uses powers of 2 as the ratios of the different current mirrors to essentially convert digital voltage or bits that are at either 0 or at the supply into a specific currents that when you drive a load and then you convert to a voltage through a current to voltage amplifier, you get an analog voltage. So hopefully, you know, you can see how that can be. I mean, the purpose is not to go into the current steering DAC architecture, but hopefully you get the gist of it. And if you are more interested, then that'd be something to do some research on and look at the circuit topology and architecture of current steering DACs. But at the heart of that technique is this of generating different currents with current mirrors and current sources. Okay. So the next thing, because I did mention R out, and that is really, we start getting then into the small signal model of the transistor. When we start mentioning that, is that we want to look at the small signal operation of these current mirrors as current amplifiers. Because if my output current is a multiple of some reference current, which I can consider my input, then really what we're talking about is about current amplification of or the current amplification capability of these circuits. And if we want to look at these circuits of the current mirrors as current amplifiers, then we have to look at the small signal model of it. So for that, the best picture, the picture that I'm going to be basing the analysis on is figure 812. Notice that there is a complementary analysis in the book in this chapter for BJTs, the same things that I'm totally ignoring, okay? So I'm not going to be covering, as always, BJTs. So what I'm going to be discussing next is based on this, here we have our current mirror, and what I'm going to be discussing is based on this series of figures. So you want to be looking at and referring to figure 8.12 of the book as I go through the next analysis. Okay. So here we're going to take a look at the small signal operation. Small signal operation of current mirrors. As current amplifiers. All right. And as we have been discussing, when we look at the small signal operation of any type of amplifier, we are interested in what? Input resistance, output resistance, and gain. So that's the main thing, okay? So if you look, and I'm assuming that you are looking at the figure. If you look at the figure, okay, and with the small signal model is that the input resistance is going to be looking into the drain and the gate of transistor 1. So the input resistance, so if I can draw quickly here, we have that goes to the other transistor here, and then this goes to ground. So the input current is right here. So the add-in is looking into the drain of Q1 and also the gate of Q1, okay? So when we do that and look at and substitute the and the other thing that is here is also the gate of Q2. So the gate of Q2 is here as well, because Q2 is here, okay? So when you look at that node, what you see is the output resistance at the drain of Q1 in parallel with the 1 over the transconductance of transistor 1, okay? But we strive, remember that we want this to be large. So we strive to do that, and we get, we do succeed. Therefore, if the output resistance of Q1 is large, then the input resistance of the amplifier as a current amplifier is just 1 over GM1. Okay? Likewise, if here we have Q2 here, the output current is here. So our output resistance is looking into there. And what we see there is the output resistance of Q2. So the output resistance of the amplifier as an amplifier is R02. Now, let's look at our gain. So next we have to look at the gain, which is our defining small signal gain, I out divided by I in, okay? With the drain voltage, with the voltage at the drain of transistor 2, okay, of 0. And that, if you look at that, again, you have to refer to the small signal to figure 8.12. that is going to be the GM of transistor 2 times VGS divided by the input current, because this is the output current, right? The output current is the VGS, okay? So the voltage here times the GM of transistor 2. That's the standard gain for this Q2, which is operating as a common source. This is IO. That's all we've done, okay? Now VGS, I have to continue in another, clear this and continue. So let me write that again. We have that but VGS is equal to the input current times the input resistance of the amplifier, of the current amplifier, okay? And we already define that input resistance. So here we have the input current, nothing's changed, times the input resistance, which is 1 over GM1 plus 1 over the output resistance of the amplifier. So you can see that this is just this here is auto 1 in parallel with GM, okay? GM1. That is Rn. So this here is this minus to the minus 1, the inverse of that, okay? But don't get confused by it. I mean, you have to be looking at the expressions that I wrote before. So I have that expression, and I can put that into this equation here for the gain. So I can get my current gain can be written as GM2 over GM1 times 1 over 1 plus 1 over GM1 at O, and that is my current gain, okay? Next we're going to recall what GM is, okay? What GM is. GM is the mobility, the capacitance of the gate of the or the oxide times the width to length ratio times the overdrive voltage.